This is Professor Ali Bumejdad from Chemistry Department at the Faculty of Science. I'm specialized in nanotechnology and surface chemistry. I'm going to talk about nitrogen-enriched date palm activated carbon for heavy metal removal. As you can see in the poster, we are targeting of removal of heavy metals from actually water by using activated carbon enriched with nitrogen element, because the presence of nitrogen in the activated carbon is very beneficial in the removal of the heavy metals. But of course we have to find a source for the activated carbon, and we know that we have in Kuwait the palm. There is a bio waste material from the palm readily available every year. So we are actually trying to use the palm raches and also the palm leaves in order to produce such activated carbon, and then we have to actually enrich it with nitrogen in order to increase the amount of nitrogen. We managed to obtain high surface area to about we reach about 1,000 meters square per gram, which is considered to be as high surface area. And with regarding the nitrogen amount, we managed to reach 8% content, which is also a high amount of nitrogen. I'll explain to you the experimental procedure. If you can see here, this will summarize the experimental procedure. We start with the bioproduct, the plant. We have to actually pyrolysis. We put it in a furnace in order to burn it under nitrogen environment. It has to be under nitrogen environment, and the oxygen should be not available at all. Otherwise, all the carbon will be converted to carbon dioxide and carbon monoxide and evaporate. So we have to make sure the nitrogen used is very highly pure gas of nitrogen. We heat it at a 600 degree, and then we obtained what we call it the carbonized carbon. Of course, this is not highly surface area, so we have to activate it by chemicals. We have used the potassium carbonate. We tested also sodium carbonate, calcium carbonate, and also we tested other chemicals like potassium hydroxide. But we found out the potassium, the first one, is giving us the highest surface area. It's actually very helpful in generating the porosity into the material. Now, in this stage, we have high surface area activated carbon, but with low amount of nitrogen, about 0.5%. So we have to treat it again chemically with chemicals that contain nitrogen. So we tested this treatment with urea, ethylamine, hexylamine, dodecyl dimethylamine, and dodecyl dimethyl ammonium bromide. We found out the best actually treatment was with urea. This one gave us 8% of nitrogen. But when we do with the DDAB, we resulted in the highest surface area activated carbon. So there is a compensation here. We have to select which one is better, or we can try both of them in terms of the metal removal, because maybe the surface area is more important than the amount of nitrogen, and maybe the opposite. So we have to try both of them and see which one is more efficient in removal of the heavy metals. So we have to do the characterization with the thermogravimetry, adsorption. We have to know the surface area and the type of pores, and of course we have to know the elemental analysis and some images to know or to see the morphology of the material. The surface chemistry, we have to do the XPS to understand the oxidation state of nitrogen. We don't know whether the nitrogen incorporated in the activated carbon, is it tertiary nitrogen or secondary nitrogen or quaternary ammonium nitrogen. So we have to know what type of chemicals we have. Of course, there will be also some oxide. We need to know, is it phenol or it is just byrene or other chemicals available in the activated carbon. We did this actually. This is the microscopy image, and I'm going to show you more importantly the surface area. This is the nitrogen adsorption. As I told you, the best result was when we use the chemicals DDAB, didodecyl dimethyl ammonium bromide. This give us the best result in terms of surface area. while the best result in terms of nitrogen absorption, in terms of nitrogen content, is actually when we use the urea treatment. Of course, after that we have to test the functional group. To study the functional group, the best technique in chemistry is actually the FTIR. It will tell us whether we have carbon-carbon double bond, carbonyl group, hydroxyl group, and other also nitrogen content groups. So we did the FTIR for both parts of the palm, and then we tested for the removal of the heavy metals. You can see here we succeeded to remove almost 98% of the heavy metals, but of course we have to control the pH. We found out the pH is very important. The lower the pH, the best the efficiency of the activated carbon. We found out pH 4 is very excellent actually for removal of the chromium +6 ion. And now in the future we want to reduce the energy consumption in this process, because you know that although our material is a waste material, so it's a green chemistry, but there is also consumption of energy during the pyrolysis of the plant. So this actually pyrolysis usually take out several hours, because you have to heat the material up to 600 degree or 800 degree. Gradually, this will take maybe 2 hours or 1 hour, and the cooling will take several hours also. So we want to reduce the time and the heat, the energy consumption. We have an idea actually to design another reactor in order to control the nitrogen temperature. Now the nitrogen temperature is going to the reactor at room temperature, but we want to heat it before we send it to the furnace. So we want to heat it to 600 degree. Nitrogen is a very stable molecule. Nothing will happen to the nitrogen, or to 800 degree. And then we send it to the activated, to the material to be activated. And this way we will actually save the time. We think we can reach up to 20 minutes or 15 minutes actually by designing this. And then we can recycle the nitrogen, cool it down, send it back to the activated carbon to reduce also the time needed for the cooling, because as I told you before, the cooling also need time. We need to reduce both the heating and cooling time. And thank you very much for listening.